Hi everybody, in this video I'm going to do the Borel Cantelli lemmas. There are two Borel Cantelli lemmas. The first one, Borel Cantelli, says the following: suppose we have events A1, A2 and so on are any events in a probability space, okay, and suppose also that the sum of their probabilities is finite. So these are the assumptions, right? Any events with summable probabilities. Then the probability of the lim sup, in other words, the probability of the intersection from 1 to infinity of the union from n to infinity of the AK is 0. That's the statement of Borel Cantelli 1. Now, what was this event again? So this told us that there are infinitely many of the AKs occurring. If the probabilities of these AKs is summable, then there is zero chance of infinitely many of them occurring. That's Borel Cantelli 1. Let me quickly prove this. So proof. Okay, and the proof is actually not very hard. Let me start with this probability and notice that this union of the AKs, so the union of the AKs, this union here is decreasing in n. This union here in green depends on n. It's a set, it's an event, that's a function of n. If you increase n, then you take the union of less and less things, and therefore this union can only be smaller and smaller. It cannot increase. Okay, and that's why these events are decreasing. Now what happens if you take the intersection of decreasing events and apply a probability on there? Well, this we know very well that in that case what you get is the limit of the probabilities of your decreasing set, which was the union from n to infinity, and this limit is taken in n. Okay, that's just continuity of probability. That's a statement we had before, and from here on it's very easy, because Boole's inequality tells us that the probability of the union can never exceed the sum of the probabilities, and therefore for every n this probability of union is less than or equal than the sum of the probabilities. And the sum, of course, is on the same index set as the union was before, so it will start from n to infinity, probability of the AKs. And now let's carefully check this sum. The assumption is that the sum from 1 to infinity is finite, and this sum is taken from n to infinity. As n goes to infinity, by the assumption, this limit must be 0. Again, this is by the assumption that the sum of the probabilities, maybe it's better to use k here, let's use k here, is finite. Okay, if the sum of the probabilities is finite, oops, now you can see this better. If the sum of the probabilities is finite, then the tail of this sum from n to infinity must go to 0. Okay, so that's the proof of Borel Cantelli 1. It's really not a very difficult statement. And let me then turn to Borel Cantelli 2. Just adding page number 1 here. So let me then turn to Borel Cantelli 2, which is almost a reverse statement to this one. It's almost the reverse statement to this one. Okay, so you can probably call this a theorem. I didn't call this a theorem, but let's call this a theorem. So Borel Cantelli 2, it's almost the reverse statement, and it goes like this. So again, let A1, A2, and so on be events in a probability space. And suppose that the sum this time is infinite. So assume that the sum of the probabilities is infinite. And I need one more assumption this time. I didn't need that before, but now I do need that. Namely, assume as well that the A's, A1, A2, and so on, are independent. This is very important. I didn't need that before, but for this one I do need independence. Okay? The statement is, the conclusion is that in this case, then the probability of the lim sup, so take the intersection of the tail union, is 1. In other words, if the probabilities are not summable, so the sum of the probabilities is infinite, and your events are independent, then almost surely with probability 1, infinitely many of them will occur. There might be gaps, there might be huge gaps, but there will be infinitely many of them which come up with probability 1. Okay, so let's prove this one. How do you prove something like this? So again, let me start with the probability of this lim sup. Take the union and to infinity ak, and this time what I want to use is independence, and independence is useful when you have intersections, whereas here I have unions. So the first step is going to be to make intersections out of unions and unions out of intersections, and the way to do that is De Morgan's law. So my first step is to take 1 minus the complement of all this complicated event intersection of the union, take the complement of all that, at the price of a 1 minus in front, and now comes De Morgan's law. De Morgan's law, which tells me that if I take a complement of an intersection, that becomes the union of the complements. So this complement goes down here, except it changes the intersection into a union. So I will start writing 1 minus probability of the union, same index set, 1 to infinity, and then the complement of this inner union. So the complement of these things here. So what happens if I take a complement of the green part? Again, it goes underneath the union, except it makes an intersection out of my union. So De Morgan's law again applied a second time gives me the intersection of the complements of the events A. Okay, so that's what I have now. Okay, now the next step is a bit similar to Borel Cantelli 1, namely I'm looking at this intersection here, the yellow one. This intersection is taking the intersection of AK complements from n up to infinity. If I increase n, then I'm taking the intersection of less and less things. Okay? Taking the intersection of less and less things as I increase n means that I'm getting smaller and smaller, larger and larger. Taking the intersection of less things means I'm getting larger, because I'm intersecting less things. So this is increasing. This is increasing in n. This is increasing in n. And what happens if I take the union of a system of increasing events, that will be equal, under the probability, that will be equal to the limit of the probabilities. So what I have here is 1 minus the limit as n goes to infinity of the probability of the intersection from n to infinity of the AK complements. Okay? So this is how you can apply De Morgan's law on this setup. And let me just add the page number here. You don't see that, I believe, on the video, but that's a page number 2. And then let's proceed with calculating this intersection. So what is going to be my next step? I have independence and I have an intersection, and that's what I wanted, because now I can use independence to calculate the probability of the intersection. So let's do that. Okay. Let me just prepare this. Alright, so let me just copy what we are having at the moment. So we're doing the proof, and we have the probability of the intersection of the union of the AKs. This is how we started, and after the calculation on the previous page, we started with this and we ended up with that. So just copying it here, 1 minus limit as n goes to infinity of the probability of the intersection of the AK complements. So far just copied from the previous page. And now applying the assumption of independence, I get 1 minus the limit as n goes to infinity of the product of the AK complement probabilities. So it's the product of k goes from n to infinity of 1 minus, well, let me just put p of AK complements for the moment being, okay, which equals to 1 minus the limit as n goes to infinity of the product of course, the probability of AK complement is 1 minus the probability of AK. And now what we see is the product of 1 minus probabilities. Now the probability of AKs, of course, the question before in the assumptions of Borel Cantelli lemmas, the question was whether the AKs are summable or not. For Borel Cantelli 2 they were not summable, for Borel Cantelli 1 they were summable. When you ask about summability, then of course the first assumption you have is that the AKs, probability of AKs will go to 0. The question is how fast they go to 0, and that's exactly what summability tells us about, and that's exactly the point where we can use the product sum lemma from the previous video. The product sum lemma tells us that when the probability of the AKs is not summable, they are too large. If they are too large, then this infinite product for every index actually is going to be equal to 0. So the product sum lemma tells us that for every n, this thing is equal to 0. That's due to the product sum lemma. Okay? Which means that for every n, this is 0, the limit of zeros is 0. So 1 minus 0 is our answer. And we're done. Probability of the lim sup is 1.